discussing an essay we just published, The Bitter Lesson About Self-Driving Cars. It contrasts Richard Sutton's bitter lesson with typical approaches that we see across the robotics world. I'm going to use Wolfram Burgard, a professor at Technical University of Nuremberg, as an example, but he's not the only one. I think, let's say this year at ICRA in Atlanta, we saw a lot of robotics people talking sort of the same book. And the contrast is the following. Richard Sutton's bitter lesson clearly states that we should not try to teach our robots how we think we learn. We should try to keep the learning as general as possible and feed them as much diverse data as possible and supply as much compute as possible. And that is the path towards learning, because nature is too complex for our human brains to understand how learning works. We think we know how we learn, we don't. It's we have a lot of examples in our language for this. For example, straight from the gut. What does that mean? That means that we make decisions that are sometimes logical frontal cortex driven, but often they're not. And then we just call it straight from the gut because we can't actually rationalize our decisions. The same applies to things like emotions. When we say we're emotional about something, what that really means in sort of cognitive science context is that our frontal cortex is not able to actually rationalize our feelings, or our thinking, our subconscious thinking, and therefore we call it emotions. So what that all means is that learning really happens in a much, much more complex way than we think that we learn. And the same applies to robotics. And that's why in the self-driving car space, we have two examples right now. We have Tesla, which is using Sutton's bitter lesson approach. And then we have Waymo, which is a Frankenstein model that uses human heuristics, sort of driven by what Wolfgang Burgard in the presentation that is attached in the essay. So check for the link there that he gave in Munich, maybe about 6 months ago. Again, it's an example. I don't want to just dwell on him too much as a person, as a researcher, but he's a very prominent researcher in the robotics space. And I think that's one of the main issues with robotics today, is that a lot of people who are taught in school, at university, in sort of the old-fashioned way, I call it the CMU way. Carnegie Mellon has, as a pioneering institution in robotics, has institutionalized this way of teaching robot or building robots in the way that we think we learn, when in fact we should be teaching our robots in a more bitter lesson way. This is not even on podcast. It's August 4, 2025. This is Krim Delco. For the day, the fund is up 2.5%. The market is up 1.5%. For the year, we're down 14%. The market is up 7.5%. We're underperforming by 21.5%. So I want to talk about the bitter lesson by Richard Sutton and this essay that we just published, which is The Bitter Lesson About Self-Driving Cars. So the message is that we should be using Sutton's insight and methodologies to teach our robots how to drive, and further on to navigate in nature. Navigating in nature requires understanding a complexity that we humans have been able to understand subconsciously, but not consciously. So we don't have a logical framework of how nature works. We don't have it in mathematics, we don't have it in physics, and we certainly don't have it in our own behavior, whether it's understanding how a Formula One driver drives 150 miles an hour through Monte Carlo, or how a baseball player hits a baseball, or how Tom Brady throws a ball in the pocket, and so on and so forth. Kelly Slater surfs an 8-footer and moves up and down the wave. Those are things that we can do, but we don't understand why it is we can do them. In other words, human heuristics are not the path towards mastering navigating nature. That's the bitter lesson. In fact, the bitter lesson goes further in stating that it's a trap to put priors in our models that are driven by human heuristics because it gives us short-term gains, but because it's not scalable in the long run, it's not going to lead to success. And I think we have a good example in the self-driving car space between Tesla and Waymo and other approaches, which are all driven, these other approaches are all driven with siloed, compartmentalized, human heuristics infused methodologies that try to mimic the way we think we learn how to drive, when in fact, we, like I said, we don't know exactly how we know how to drive. Sutton talks about this in the bitter lesson and also in many other presentations. Actually, there's a presentation that he gave in 2017, so this is 2 years before the essay, and I encourage people to listen to this presentation because it's really interesting to see how his thinking is galvanizing around an essay that will be written 2 years after the presentation. In that presentation, which he gave at Google DeepMind, he spoke about the problem of the human heuristics. The problem with them is that they're not very precise. So let's say we think that we localize ourselves when we drive, and we think that we have a good sense for where the curb is and where the road is, and that's most likely not true. We have a much better feeling for where we are in sort of the subconscious, and what that actually is, we don't know. What gives us this unbelievable sense for space and physics? Another example is when you surf a wave or when you ski. I mean, the actual physics of that particular situation, think about it. You're almost vertical, you're going down a wave, or in the skiing example, you're going down a mountain and you're not falling, you're not slipping, you're not doing any of that stuff. Your senses are amazing, and you're certainly not doing planning, localizing, mapping, and all that stuff that the robotics people came up with. What they came up with, and that started at CMU in earnest in the early 2000s, but of course was rooted in earlier approaches in control theory and things like that. What started there was an approach, an attempt to understand how we think we learn, when in fact we don't know how we actually learn. Now, we can look at the history of AI, which has been always bitter lesson, which is there has always been approaches, whether it's in natural language processing, image recognition. Let's take image recognition, which was the first breakthrough in 2012. So image recognition has been working for years before ImageNet in 2012 as a sort of discipline within symbolic logic. We were trying to understand what is the structure of an image and what is the structure of a cat. How do we distinguish a cat from a mouse? Things like that. And then, of course, neural nets came along, and ImageNet and unbiased general methods, training and large data sets yielded much better results. Fast forward 2000, maybe 23, ChatGPT comes out, which is basically solves the Turing problem, the Turing test, excuse me, and solves the natural language processing model. Again, it does that not by understanding language, not by using linguistics. It does that just by using vast amounts of data. Of course, it uses methodologies that are more suited towards understanding what language is, such as transformers. But the point that Sutton is making in the essay is we should use our methods to learn and not use our way that we think we learn to learn. So we use our method. We should think about the methods that we could use so our models can learn. I think I finished the essay with the Sutton makes a very important point also in that presentation, which is, look, just bitter lessening everything now is not the solution, because we are also not aware of the bottlenecks very often. For example, in supervised learning, we understood very quickly that the bottleneck was annotation. In unsupervised learning, we realized very quickly that the bottleneck is compute and memory and things like that. And I think as we advance with compute, such as Blackwell and the next generations of NVIDIA, we will probably have better compute and memory availability and all that. But What we don't have is data. So data is now becoming the bottleneck. And the problem with data is, of course, how do you generate rollouts? For example, offline reinforcement learning, or even self-driving cars. We have, Tesla has been able to train itself on a vast amount of videos that were taken while the car was driving, driven by its customers. So we have millions and millions of miles. But of course, ideally, we want to have even more data, particularly data that challenges physics, challenges also. One of the biggest innovations also, I think, in reinforcement learning has been the fact that we should also have a lot of bad examples so we can learn even better how to drive. So we should have actually, let's say, many rollouts of situations where cars hit pedestrians, so we learn how not to hit them. That would be much better than if we just learn how not to hit them from actual driving. Now, of course, we can't mimic that in the real world, but what we could do is we could mimic it in simulation. So simulation is the key forward in terms of unbottlenecking the data. One last thing I want to mention is the problem of eval. I think as we go forward also with superhuman intelligence, we need to find better evaluation models, because iterative learning, such as the bitter lesson predicts, is the path towards superhuman intelligence. That iterative learning requires evaluation. Like if we want to iterate around something, we have to understand what is better and what is not better, right? We have to have an eval. And the best way forward, there's two ways you can do evaluation. One is sort of the Monte Carlo method, which is you kind of try to simulate billions of scenarios and weigh them with some sort of reward function, and then just see which trajectory gives you the best value. Or you can do it iteratively, sort of in a binary way. You just do thumbs up, thumbs down. But in both cases, you have to have a judgment of what is good and what is bad. And I think that in itself is a big question. I think that's why, let's say, Sergey's presentation at the Agentic Summit at Berkeley was about the offline reinforcement learning, which is inverse reinforcement learning, really. So in order for us to understand what we want, we should just look at behavior of people and then infer reward functions from there. So what that means in a self-driving car context would be something along the lines of trying to run scenarios of how a car reacts in certain situations, and then get the behavior or the judgment of people, maybe in some sort of reinforcement learning by human feedback way, or reinforcement learning by validation or something like that, where we can just say, okay, in this case you did better than in that case. So because the car has to, like every model has to eventually be taught what's better and what's worse so it can improve. So to summarize, the bitter lesson about self-driving cars is a positive connotation, because the bitter lesson itself is a positive way. It's a solution to a question, which is how can we get superhuman intelligence? We can get it with general models and vast amounts of data, and not by trying to teach robots how we think we learn, but generate methods that teach them how to learn without us interfering with priors. Thank you.